So thank you all for being here. Thank you for inviting me to speak here. My name is Chance. I work on the privacy and scaling team at the Ethereum Foundation. And today I want to talk to you about building robust user experiences for anonymous applications as well as anonymous user data. So this talk is going to be split into two parts. First, I'm going to talk about what anonymous data is and some strategies for implementing it. And then I'm going to go over some example applications that we could build right now today with the technology that we have. So let's get into it. So first, let's start with the definition of what anonymous user data is. So we want to define users as an entity that controls a private key. And then we'll say that every user needs to have their own set of data. So every user needs to have, say, 1 kilobyte of private storage. And so we want applications to be able to change data for their users without knowing the user's identity. And so in UniRep, we're able to do this using short-lived identifiers called epoch keys that change over time. And the idea here is the user presents an epoch key to the application along with a proof of something, and then the application is able to change the user data for the user anonymously. And then we also need to be able to prove the data anonymously to the application, potentially apply some logic to it in ZK, and we're able to do that. So we use ZK for most of these operations, but I imagine there are other strategies for implementing these types of systems. So once we have anonymous user data, we can build anonymous applications. And so we want anonymous applications to be applications where user identity is not always known. So critically, the user should be able to reveal their identity in some cases and continue to use the application anonymously afterward, as well as not reveal their actions in the past. So for example, they might want to reveal their identity to do identity verification or to reveal a pseudonym associated with a single post. They should be able to do that without revealing their identity in the past and in the future. And differently from normal applications, anonymous applications don't involve a user signing in. Instead, the user sort of lazily provides proof of their identity when they want to perform certain actions. So for example, if a user wants to make a post into a certain group, they're going to make a proof that they're a member of the group and then sign their post and give that to the application. And the application doesn't need to know anything else about the user. They're able to simply put the post in the group based on that proof alone. So instead of signing in at the beginning of a session, the user never signs in and just kind of uses the application. So this leads to the question, can we build anonymous applications with the same user experience as non-anonymous applications? And so another way to put this is, could we build a Facebook where users are anonymous to the platform, or could we build an Amazon where users are anonymous to the platform? And I think the answer to this is yes. Maybe not right now, but at some point in the near future. So I think we should also ask, like, are anonymous applications even worth building? And so I want to identify some sort of pros of anonymous applications versus non-anonymous applications. So the first is that this sort of negates the risk of data being hacked from the application or data being monetized or sold without the user's consent, because the application isn't able to determine what data belongs to what users. The user also gets more identity flexibility. So they can be anonymous, they can be pseudonymous, they can identify themselves, and they can change that over time with each action. And they can even retroactively change it in the future. And then the biggest one is that we get more interoperability with anonymous applications. Because user data has to be stored in a public place for the user to retrieve it, any application can build proofs on behalf of the user and then interoperate with the data that belongs to some application. And so this is very different than Web 2 applications, because if, for example, I wanted to use an alternative front end for Twitter, not only do I have to give permission to this third-party application, but I have to get permission from Twitter to use this third-party application. So users don't actually own their data, they more lease it from Web 2 applications. They require permission from the application, which I think is wrong. Users should be the only ones that have custody of their data. And so we end up with like fewer walled gardens as a result of this. We can build applications that interoperate, extend the features, stuff like that. And then the last one that was like sort of specific to me is, I was just thinking, I haven't used Facebook in like 5 years, but I haven't deleted my data from the platform because it's a huge burden, right? I need to go back up the data potentially, decide whether or not I want to keep it, what I want to do with it. But at the same time, I don't really want Facebook to continue having access to the data, doing whatever they're doing with it. And so if Facebook was an anonymous identity platform, I wouldn't have to worry about deleting my data because it would be encrypted at rest and they wouldn't be able to access it in the first place. So I could just leave and not worry about my data, not worrying about deleting it. So what are the cons of anonymous applications? Easily the biggest one is complexity. These things are complex and difficult to implement. The developer experience is very rough right now for ZK, even for blockchain to some extent, as well as like you need audits and stuff like that. And then you also end up with a potential false sense of security. So you're not necessarily vulnerable to the platform getting hacked, but you are vulnerable to, or you're potentially vulnerable to flaws in the protocol implementation or failures of the cryptography itself. So users need to keep that in mind, platforms need to keep that in mind. So I work on a protocol called UniRep, which is short for Universal Reputation, and I'm going to give a high-level overview of what it is. This is going to stay like pretty non-technical, I think. So in the current implementation, we allow 200 bytes of data to be stored per user, and this data can be retrieved and operated on in ZK. As I said before, applications can change the data anonymously, and they do so using ephemeral identifiers called epoch keys. The only thing that you really need to know about UniRep for this talk is that epoch keys anonymously identify users and can be used to change data. And like I said, users can prove their user data anonymously within ZK, and applications can extend the logic. And so the two important properties of UniRep as a data storage system is that changing data or mutating user data requires write access to the blockchain. So you have to send a transaction in order to change a user's data. But verifying user data only requires read access to the blockchain. So this protocol is well suited for applications that want to do few writes but many reads, because you can scale read operations and proof operations independently of the blockchain. So you're not subject to the limitations of 10 transactions per second or whatever we're currently at. So let's talk about some example applications that we could build right now today with UniRep. So the first one's a fun one. It's an anonymous payment/transaction system that is right on top of Ethereum. So you'd like Zcash or Monero, but you don't have to leave the blockchain. So we want to do a few things. We want to allow Ethereum addresses to send to epoch keys, which would be a deposit. We want to allow epoch keys to spend to other epoch keys, which would be an anonymous transaction. And we want epoch keys to be able to withdraw to Ethereum addresses, which would also be anonymous. So this is what the user data would look like. We tend to define like signed integers as two different unsigned integers, and we would take the balance as the positive balance minus the negative balance. And we do this so we can use only addition operations in the system. And so this is what a deposit flow would look like for this application. So we'll have an application contract that implements the logic of this system. And when a user wants to deposit, they will send their Ether along with a ZK proof containing an epoch key. And then the application contract will verify it and then update the user data such that they have positive Ether 2 and negative Ether 0. And now the user has a balance within the system. And the application contract just custodies the Ether in this case. So how do we want to implement sending Ether? It's very simple, actually. We just make a ZK proof that contains the two epoch key, the amount the user wants to spend, as well as a fee. And this can also be sent to an Ethereum address. And so the reason we include a fee in this system is so that the user doesn't have to broadcast the transaction themselves. So they can just make the ZK proof and then give it to the public, and as long as the fee is greater than the expected transaction cost, a third party will broadcast it to collect the profit from the transaction. And so the user data after this transaction is processed looks like this: positive Ether 2, negative Ether 1.01. And inside the circuits, we verify that the user isn't spending more than their net balance. But a problem with this system is that it's not super legal, right? Tornado Cash does effectively this, and they got sanctioned by the US government. So we wanted to extend this system to add identity verification for the users. So we simply extend the user data to look like this. We add a verified flag inside the data, and then we go to some institution like Coinbase and we say, hey, please do identity verification for our users. So now, when a user wants to use the application, they first submit their identity documents along with an epoch key to Coinbase. And then Coinbase takes a few days, they review the documents, and they say, okay, this person's good to go. And they attest to that epoch key, setting verified equals to 1. We go back and we change this sending transaction to verify that anyone sending Ether has verified equals 1 in their user data before they can send a transaction. And so at that point, we have identity verification for anonymous transactions. And so say that we wanted to extend this and we wanted to actually make users verify every 6 months, for example. This is also very simple. We add a verified @ flag, which is a simple timestamp of when the user was last verified. And in the ZK proof, we check that verified @ is greater than a point in time 6 months in the past. And then you have rolling identity verification for an anonymous transaction system. So another example is anonymous group chats for Ethereum addressees. So some interesting example groups that we can make are like the Ethereum 2 stakers, ERC20 721 owners, or like a simple group like addressees that sent a transaction before 2018. And we want to allow them to anonymously and publicly chat and provide a proof of address control with every message. So every message will have these 3 things: a hash of the message, a proof of address ownership, as well as a proof that their address exists in the group that they're messaging within. And so we can do this using a set of circuits called Circom ECDSA, which is developed by 0xPark. But the problem is that using those circuits takes about 5 minutes to make a proof using ECDSA. So this isn't a very instant messaging system. This is a messaging system that takes 5 minutes per message. So how can we fix this using anonymous user data? What we do is we make this 5-minute proof once, and then we store it in the user data as just like address is this value. And now when a user wants to send a message in this group, they instead make a proof of user data as well as a proof of group membership, and that instead takes about 1 second. But you still have the guarantees that the user controls the address and you retain anonymity for every message. And so I was thinking about this talk, and I thought it would be lame if I just showed up and talked about theoretical use cases. So I went ahead and built exactly what I described here, and you can go use it at zketh.io. I made a group for every address that purchased an ENS domain. So if you have an ENS domain, you can go message in that group. And you can also go make your own groups by just supplying a list of Ethereum addressees. And there's also like a short circuit, like if you don't want to make the 5-minute proof, you can reveal your address on sign up and then send anonymous messages after that. That's just like a user experience thing. And I'll put this link up again at the end. So these last 2 examples were maybe like interesting toys, but I don't think they're like robust user experience or user applications. So let's try to like come up with an application that's a little bit more robust. So let's develop an online marketplace that works sort of like Amazon. It just sells items to users. And we want the users to be able to do 4 things, or we want the application to do 4 things. We want users to be able to buy things. We want the application to store the purchase history for each user. We want the application to be able to recommend items based on the purchase history. And we want the user to be able to create and save lists of items. So this is what a proof of purchase would look like. Let's do this first. So the user would assume that we have a similar payment system to what I described earlier. They would put a payment of 1 Ether in a ZK proof, and then they would also use this ZK proof to sign the encrypted purchase list as well as encrypted delivery address that they give to the platform. This would be asymmetrically encrypted using the platform's private key. And then they would give this proof to the online marketplace, and the online marketplace would say, okay, they want to purchase these items. Are they in stock? If they are, then they say they process the proof and create a transaction or create a purchase. So this is what the user data would look like in this application. So the first 2 fields are the most important. What we have first is this history root. And the idea here is we only have 200 bytes of user data that we can anonymously write to. So what we need to do is figure out a way to sort of nest data within this. So what we can do is put the list of purchases the user has historically made in a Merkle tree, and then put the root of that Merkle tree in the user data. And then we can extend the ZK proof system to prove that purchases exist in this tree and to ultimately update the tree and the history root. And then the saved hash is, so we want the user to be able to create and save lists of items. The platform doesn't necessarily need to verify this. Like if the user wants to create a list of invalid items or non-existent items, they can do that. So what we do here is we'll symmetrically encrypt the lists that the user creates and then just put the hash in there without much verification. So let's look at the history root a little bit more. This is what the history tree would look like. So every time the user makes a purchase, they're going to update this tree in ZK and add a purchase element and a random element. And so the reason that they add a random element is so that an outside observer cannot like brute force construct the tree, because all of these purchase hashes are going to be public data. So if there are only 100,000 public hashes, you could just try to combine them all in different combinations and figure out like which root matches the root that a user has posted. And so if they add a secret random element, then you can't do this because you would have to break the hash function. So yeah, the user updates this tree in ZK, and their history root gets updated. And so user data is stored on the Ethereum blockchain as events. So the user just iterates over the events and constructs their data. But in the case of like this history tree, these would need to be stored, these leaves would need to be stored in some sort of public storage place like IPFS or Arweave, something like that. Right. And then how do we do recommended items based on the purchase history? So the key here is that instead of the server recommending items to the user is going to construct their purchase history within the web browser. So they're going to go look at the Ethereum blockchain, they're going to go look at IPFS and construct their purchase history. And then in the client, they can calculate recommended items. They can say, okay, this user has purchased like a lot of cleaning supplies, recommend cleaning supplies to me, and ask the server to do that, for example. And so instead of the server doing all these things for the user, the client ends up doing these things for themselves, and the data stays more private. Yeah, that's about it. These are some links. So ZK-ETH is this Ethereum address chat thing. We also have like a demo online, which is a demo attester where you can set data for yourself and just see how the system operates. And we have an explorer for the system as well, so you can see like all of the applications that are registered as well as the operations that they're doing and get a little more insight into what's happening. And this QR code is to our GitHub. Yeah, that's it. Thank you.